Hello everyone, welcome to lecture 17 of the online course on modern display technologies, flat panel display. Today's lecture will be on the effects of electric field on liquid crystals. So here's the lecture outline. We have already discussed some of these effects on liquid crystals, such as the dielectric interaction in nematic liquid crystal. We have discussed about the reorientation under dielectric interaction and the field induced orientational order. In this lecture, we will be focusing mainly on the flexoelectric effect, and then we will see this effect in nematic liquid crystals and cholesteric liquid crystals. We will also discuss about the ferroelectric liquid crystals, discuss about the symmetry and polarization, tilt angle and polarization. We will go for surface stabilization, and then we will see the effect in those ferroelectric liquid crystals, and finally we will see the electroclinic effect in chiral smectic liquid crystals. So let's begin our discussion today with this topic, that is the effect of liquid crystals on effect of electric field on liquid crystals. So we will be mainly focusing on the flexoelectric effect. So what is this flexoelectric effect? So the uniform uniaxial nematic liquid crystals, they basically show non-polar cylindrical symmetry without any external electric field. Now in those kind of liquid crystals where the molecules have a permanent dipole along the long molecular axis, something like this, okay, you will see that the potential for the orientation of the dipole has reflection symmetry about the plane that is perpendicular to the director and cap. So this will be the kind of director and cap along the vertical direction. So the dipoles basically have reflection symmetry about this plane. Now in this particular case, you can see that the dipoles are equally likely to align parallel or anti-parallel to the director and cap. So what you see, that there will be no net spontaneous polarization that will be occurring, because the parallel and anti-parallel will try to cancel out each other. Now if you consider the molecules where the permanent dipole is basically perpendicular to the long molecular axis, so this is the long molecular axis. So in case B, you are seeing that the dipole is basically, the permanent dipole is basically perpendicular to that long molecular axis. So what you see here is the potential for orientation of the dipole is cylindrically symmetric around the director. Okay, so the director will be in this direction, but you can understand that the dipoles can basically point equally in any direction that is perpendicular to the director, right? So in that case, here again no net polarization can be seen. So your polarization is again 0 in the uniform state. Now let us look into the case where there will be director deformation. In non-uniform liquid crystals, this kind of molecular symmetry can be broken. So you can see for pear-shaped molecules like this, okay, so the splay deformation basically breaks the reflection symmetry about the plane perpendicular to the director. Okay, so here you see it is becoming like these are pear-shaped molecules, and this is the splay deformation that is happening. So in that case, the dipoles along the molecular axis basically now prefer one direction. Okay, so what is happening, a spontaneous polarization can now appear, that is again along the direction of the director, that is n cap. For banana shaped molecules like this, okay, earlier we have seen this is the case, okay, but now whenever there is a band deformation, that band deformation basically breaks the rotational symmetry. So here again all the dipoles, the molecular dipoles who are perpendicular to the molecular axis, they basically prefer a particular transverse direction. So you see they all get aligned, okay, and then again a spontaneous polarization can appear along this bend direction. So this kind of polarization that you see as a result of deformation, okay, so you can also say that the deformation induced polarization in a nematic liquid crystal is basically called the flexoelectric effect, okay, and it was first proposed by Mayer, and the total flexoelectric polarization can be written as PF will be ES n divergence of n plus EB n cross curl of n. So what is ES? It is basically the coefficient, splay flexoelectric coefficient, and EB is basically the bend flexoelectric coefficient, and n vector you all know that is basically the director vector. So this ES and EB, these coefficients will have units of volt, and the sign can be plus or minus depending on the molecular structure. So what we understood, that this is the flexoelectric effect in nematic liquid crystals. So what is the physical meaning of this equation? It tells you that the splay deformation produces polarization along the director. That's why it is in the same direction. It's a dot product. When you see the bend one, that is basically, that bend deformation basically produces polarization along the n cross curl of n, okay. And other important thing is that the sign and the magnitude of these two coefficients, they basically depend on the molecular shape asymmetry, permanent dipole moment, and also the molecular structure. So when an electric field E is applied to a cell with flexoelectric liquid crystal, any small perturbation of the director that can be coming from the thermal fluctuations or maybe from the boundary, okay, that can induce this PF, okay, which basically interacts with electric field, lowering the energy. So that may lead to instability. So the interaction energy with an electric field E can be written as minus PF into E. So it is basically minus PF dot E, because this is in the vector form, polarization as well as the electric field. So how do you compute the stability under electric field? So we have seen that without any external electric field, uniform director configuration is basically stable. So you are not seeing any flexoelectric polarization getting induced when there is no electric field, right? Now when an electric field is applied, small director fluctuation can create polarization, and this polarization basically interacts with the electric field. Also the free energy will decrease, that will make the deformation grow. So the final state is basically decided from a competition between the two forces. One is the electric torque, which is basically linearly proportional to the deformation. So that basically promotes the deformation, and then you have the elastic torque, which is proportional to the square of the deformation, and that basically resists the deformation. So in the end, the system basically reaches an equilibrium state where this electric torque and the elastic torque, they basically balance each other. So now let us look into an band geometry experiment. So this is how it works, that flexoelectric band deformation can be studied using a cell where you have homeotropic alignment layers, weak anchoring strength, and you have liquid crystal with small negative dielectric anisotropy delta epsilon. Okay. So initially, without any electric field, you will see that the liquid crystal molecules, they basically remain in a uniform homeotropic state. Okay. Now in this orientation, so this is your x-axis you have marked, and now let us apply an electric field along the minus x direction like this. Okay. So there is height of the cell is h, so this is the center 0, this is h by 2, okay. Now what you see that because of this electric field, a band deformation basically appears, and that is coming from the flexoelectric effect. Now we already mentioned that we took a liquid crystal which has got a small negative dielectric anisotropy delta epsilon. Now since this delta epsilon is small, the dielectric energy can be neglected. So here the free energy density becomes mainly a balance between the band elastic energy and the flexoelectric coupling energy. Now that is for band. So this is an experiment that is shown for splay. So splay geometry experiment is shown here in figure 4. So here you basically see that you again take a liquid crystal setup with small positive dielectric anisotropy delta epsilon. Okay. So in the absence of an electric field, here again we see that the liquid crystals basically remain in a uniform homogeneous state, and the director is aligned parallel to the substrate surface. That was the same in the previous case as well. Now if you mark the axis like this, the director is in the x direction and you apply the electric field also along that direction. So here what happens, a splay deformation is produced. Okay, and this deformation occurs mainly because of the flexoelectric effect. So in this kind of geometry, the induced polarization is mainly associated with the splay term. Okay, so you can write PF equals ES n and then divergence of n. So the splay geometry is mainly used to study the splay flexoelectric coefficient ES. Clear? Okay. Now let us go into the details of the flexoelectric effect in cholesteric liquid crystals. So in this particular discussion, we will focus only on the cholesteric liquid crystals. Okay. So it is understood that this particular effect, flexoelectric effect, also occurs in this kind of cholesteric liquid crystals, and this is because the local orientational order of this cholesteric liquid crystal is similar to that of the pneumatic liquid crystals. So both of them basically experience similar kind of effect. Now you consider a cell, cholesteric cell. In this figure A, you can see that there are two parallel substrates and then you have transparent electrodes. Okay, and then you have homogeneous alignment layer coated in the inner substrate surfaces. Okay, so this is x direction and this is the z direction. Okay, now so this is basically the xz plane. Okay, and this is your xy plane. Okay, so that's how you can actually see that the helical axis is basically the parallel to the substrates. Okay, when this liquid crystal is basically cooled from the isotropic phase under an external electric field. So you basically see that the helical axis, okay, is parallel to the substrate, and you can also see that it is uniformly aligned along the x axis by the alignment layer. So you can see in this A and B the orientation of the cholesteric liquid crystals. Okay, so this we have seen. Now let us apply. So these two were the case for applied electric field is not there, so it's 0. So now let us apply the electric field. So when you apply an electric field across cell along the z direction, okay, that means along this particular direction, so you bring in this E. So or you can also see what happens in this xy diagram. So you are basically having the field that goes into the plane of this screen. So you can write E equals Ez, basically it is going along the z direction. So what you understand that the helical structure remains preserved and the pitch also remains changed, and you will see that now the helical axis also remains parallel to the substrate. However, because of the boundary, okay, now there will be incompatibility between the helical structure and the boundary. So, near the surface the directed deformation will occur, and that is where the flexoelectric polarization will get induced. So, you can see that because of this there is a tilt in the angle. Okay. So, this applied electric field basically interacts with this induced polarization which is coming from the flexoelectric effect, and this interaction basically causes the in-plane component, that is the in-plane component of the director, to tilt, and this tilt further increases director distortion, and that will also induce additional polarization. So, it started from this incompatibility of the helical structure with the planar boundary condition, and then the director deformation happens near the surface, and because of that flexoelectric polarization is getting induced, and the incident or the applied electric field basically interacts with that induced polarization, and this interaction basically tilt the in-plane component of the director. So, what is happening, that tilt is further increasing the director distortion, and that induces additional polarization. So, the effect gets amplified like that. So, if you want to see, so this is basically the optic axis O that has been marked, and these are the components of the liquid crystal director in the, so normally the director is in N, okay, that is perpendicular one, but then when it is in the distorted shape, you can break it into Nx, Ny and Nz components. So, Nx is sin phi sin q naught x, and y will be minus cos phi sin q naught x, and nz will be cos q naught x. Now, what are these quantities? You need to understand that psi basically tells you about the tilt angle of the in-plane director component. So, earlier it was flat, now it has become like this. So, this angle is basically psi, and q naught is basically the helical wave number. Okay. And because of this orientation, the optic axis which was earlier along this director, that also now gets tilted by the same angle. So, optic axis earlier was this one, has got now tilted to this. So, that tilt is again by the same angle psi. Okay. So, in this case you can write the induced flexoelectric polarization can be given as Pf equals Es n divergence of n plus Eb n cross curl of n. So, this equation we have already seen earlier. So, here you can use the approximation that Es and Eb are equal, and in that case the induced polarization becomes Pf equals Es q naught sin psi z. So, what you have seen from this equation, that the induced polarization is basically directed along the applied electric field direction, because the electric field was also applied along the z direction, and the induced polarization that you see here is also seen in the same direction. So, now let us calculate the free energy density. So, in this kind of liquid crystal, cholesteric liquid crystals, the free energy density F will include the splay elastic energy, the twist elastic energy, and the flexoelectric coupling energy. So, F, which is the free energy density, can now be written as half K11 Q naught square sin square psi plus half K22 Q naught minus Q naught cos phi whole square minus Es Q naught E sin y. So, this is the term that you have just seen that represents the flexoelectric coupling energy. Now, let us assume that the induced tilt is very small. So your psi is very small. So in the small angle limit, you can write sine psi equals psi and 1 minus cos psi. So cos psi becomes 1, so that will become 0. So in that case, this particular free energy density equation can be simplified to this form. So here, instead of sine square psi, you can simply write psi square. So you get half k11 q naught square psi square. Now this term becomes 0, so this goes out, and this only becomes Es q naught E psi. Okay. So this is the free energy density when the tilt angle is very small. Now what is this angle psi? How do you calculate this? So let us find out the field induced tilt angle. So minimizing the free energy with respect to psi, you can basically take the derivative of this with respect to psi and equate it 0. Okay, and you can find that psi equals Es E divided by k11 q naught. So what you see from this particular relationship is that the tilt angle is linearly proportional to the applied electric field, and reversing the polarity of the applied voltage. So Es can be positive or negative depending on the way you are applying the voltage. So you can change the polarity of this, so that can basically change the direction of the tilt of the optical axis, whether this side or this side. Okay. Now when the electric field is switched off, the tilt angle relaxes as psi equals psi naught into the power minus t by tau. So you basically remove the electric field, so the tilt angle will also slowly relax and the tilt will disappear over some time. Okay, so that time is called the relaxation time, in which this becomes like it basically relaxes exponentially. So psi equals psi naught into the power minus t by tau. So from this you can find out the relaxation time, which is basically gamma divided by k11 q naught square. Okay, so typically for the short pitch cholesteric liquid crystals, the relaxation time can be as small as 100 microsecond. So it is pretty fast. So do we have any kind of electro-optic application from this? The answer is yes. The flexoelectric effect in these cholesteric liquid crystals can be used for light intensity modulation, and that is why we are studying it here, because we want to modulate light intensity in our displays. So when the cholesteric liquid crystal cell is placed between two cross polarizers, so then you apply an electric field which can basically tilt the optical axis, and this can essentially modulate or change the transmitted light's intensity. So what you can see, that because the response time is very fast, 100 microsecond, so you can use this cholesteric flexoelectric switching for very fast electro-optical modulation. So with that we conclude this lecture, and we'll be covering the effects of further discussion on this electric field effect on liquid crystals in the next slide. If you have any doubt regarding this, you can drop an email to this email address mentioning the course name on the subject line. Thank you.